So, welcome in this quite warm room here at first. Yes, my name is Wolfgang from Bestenbostel. I'm a failure analysis expert from Airbus in Germany. Today I want to show you a little bit about what we are doing in quantitative fatigue fracture analysis. At first, why fatigue fracture analysis in general? For us, it's the basic information of the estimated crack growth. It's the fatigue test validation and also a contribution for the preparation of inspection regimes. This means the inspection during in-service as well as the first part inspection. It's required and useful for our stress and design departments and really crucial for airworthiness and at least the arising repair costs and repair and service costs. Yes, the issue is that there's still a lack in the definition and harmonization. We want to define and harmonize these analysis procedures at group level as well as in the European aerospace industry at the end. Since years now, and okay, but what is the basic information of the fatigue fracture analysis? I know a lot of people know it very well, but again, here we see it first. We can see the crack start area, the location of the crack starting point, if there are multiple crack starts, if there is multiple site damage and things like that. We can answer the question why the crack started. Is there a mechanical damage to the crack start? Is there corrosion? Are there inhomogeneities of the microstructure? And other things here, for example, we see a typical corrosion pit at a crack start. And the type of loading, last but not least, this means constant or variable amplitude loading in fatigue, or the loading mode is bending, is shear, mode 1, mode 2, whatever, mixed mode. So what is can additional derived from quantitative fatigue fracture analysis? So first, we can see the crack growth behavior. This is at least the ADN versus the crack length at the end. Here you can see it's a static growth, but it's not necessarily so, especially in components. They can have a low transition to other areas. And the same here, you can see, for example, it's not really constant in this case, a crack growth curve. And if you know the absolute load cycles, you can also from there estimate the initiation time, which are both very, very, very valuable things for our stress departments. We're doing this by the interpretation of the fracture morphologies, like the crack length, which is often a big discussion, and also the cause of the fracture itself. The classical method to do that at the moment is the fatigue situation counting. Just to explain a little bit the general procedure, if you have here the schematic view of a fatigue fracture surface with the crack starting point and here in these beach marks or whatever areas, whatever it should be in this case. And we start here with defining a measurement direction, which starts at the crack starting point. And then the striation spacing is measured independent of the crack length. See here, the very first beginning, there is narrow distances, and then it's measured in different areas. Typically, as I said, typically the spacing grows, but it's not necessarily so. And then we come up to the end. Yes, the evaluation, we did different attempts for the evaluation, and but at the end, finally, the most simple method, the step analysis, delivers the best results we will at least afford it at the end. It's a very simple mathematics. It's a calculation of the crack propagation curve as sequential attempt. At the end, here's nothing more that the ADN versus crack length and resulting in the crack propagation curve as I've shown before. Yes, where are the problems? The appearance of the fatigue situation. There are a lot of influencing factors like load, environment, material, and with different parameters which are influencing that. This leads at the end to numberless variations of fatigues, of possible manifestations of the fatigue situations. And we have the problem that the manual accounting is really challenging at the end. It's really a very time-consuming process. Sometimes if you have larger or complicated samples, we count one person up to 2 days on one fracture surface. Yes, and that's also a very important point, that the link between the pattern and the load cycles, because of these possible manifestations, has to be performed with precautions, that we are always in closely with our stress analysis departments concerning the creation counting at the end. As it was in the beginning kind of Wild West with the creation counting, we started with round robins. Altogether 7 laboratories from within Airbus from 4 different countries started different round robins now. They were all made at the beginning under constant, up to now under constant load on 3 different materials. This is aluminum to titanium and a high strength steel. And here, for example, we see first evaluation and results of the round robin on an aluminum specimen. You see it's just a CT specimen, where we knew it's a fracture growth specimen. We knew the fracture growth behavior. And this is the blue line here in this case, dark blue line. And you see the standard deviation of the counted numbers of the cycle is active, is below 5% for aluminum. We tend to receive slightly lower values compared to basis, just one comes up to the end. But this is really a problem, especially at the end. You get such large distances of the fatigue striations, and you get a mix-up with slip lines, and it's really hard to interpret the transition between the real drag end and what you see in the scanning electron microscope at the end, and what you can see here on the machine itself. So yes, as I said, it's really time consuming. So we started with new developments. The last time is really to start with automatic striation counting. The first demonstrator called the Sandhopper, because it's a partly automated tool which supports only manual taking images by clicking and counting, and the end and the final aim is really to produce the so-called night cruiser, which is a fully automated data acquisition and image analysis system with an autonomously controlled scanning electron microscope, where I really do in the evening my specimen in, and the next morning I get the complete counting completely finished and completely automated. There we are somewhere here in between at the moment. To see the Sandhopper, which is all finished and which is also in use in all our laboratories. It's a very simple tool at the end. We have, as I said before, we have to acquire the pictures as up to now, but it's very simple because I just have to make a picture of the track start, and then I follow the line and make as much pictures as I want and as possible, and I have nothing more to do. In the first step, I load these pictures inside the tool. It automatically views the stage image position relatively to each other and calculate, and then in just clicking, the tool automatically measures the distances or the spacing of the striations. Because it recognizes automatically the striation. It's a quite complicated mathematics. In this case, it's really complicated mathematics behind. And it's also patented. And yes, at the end, you can see in parallel the ADN curve. It's built up just to control yourself, what you're measuring in this case. And at the end, it's an automatic report, including all the information of the striation counting. We evaluated this with a lot of independent data sets, and we saw really it's highly reproducible results. It's really operator independent. As I said, we have made different data sets. My little 7-year-old daughter tried it and had the same result as myself. So it was really operator independent. And at the end, as I said, very fast as procedure, because it really 20% of that what we need normally in the striation counting. So another thing what we tried in the last years is the fractographic analysis by non-contact 3D optical topography measurements. This is nothing more than the evaluation of the crack growth rate through roughness measurements. And we got really good results between the fatigue crack growth rate and the roughness for 2 steel alloys. And it was really good that we could also evaluate crack growth rates in these areas, which are in fact a black spot for the striation counting, because in the very first beginning, there are no striations. And so in these areas, it's possible to use this tool. Nevertheless, the limitations are that the method is based on reference curves, which has to be produced for each material, which each variation. This means if there's a microstructural variation, this means it's temper condition, if there are residual stress, whatever. There are really large variations of possible things. And in addition, the R ratio must be known. From that, the tool is not, or the method is not really often used, sometimes, but not really often. And the future. Yes, that's what I not mentioned up to now, is the variable amplitude loading, which covers 50%, to be honest. And because it is really much more difficult as the constant amplitude load. And here the loop of the stress analysis is even more important. And you can here distinct also between regular patterns and statistical patterns. Statistical patterns as they typically arise in failure analysis from in-service parts, but also regular patterns as we also have very often, because we have also often test parts from our full-scale testing or from the testing departments, just to see there the growth of the fatigue cracks. In case of statistical patterns today, it's mostly covered by standard counting method. Future, as I said, we are on our way to automate the system, and then really to see, make thousands of pictures or hundreds of pictures, whatever, and come really to a simple counting of the situations, what a machine can do, what a man not can do. And the other point is really with regular patterns. It's today very extensive visual pattern recognized, really with printing out, comparing the patterns and finding how it evolves. And in addition, we use the fracture mechanics tool Prefas, especially to interpolate to the correct start and how to interpret the results. But also here in the future, pattern recognition based in this case on artificial intelligence is planning or ongoing. So to conclude, the quantitative fracture analysis is really crucial for us in the Airbus aircraft industry. The fatigue striation counting is at present the standard process, yes, and I think this will not change so fast. And the methodology validated by round robins for different materials. From that, first standard, as far as knows, the first standard within the industry is the Airbus industry test method, fractographic analysis of fatigue fractures, striation counting method. Yes, as I said, these 3D topographic measures can only be used as supplementary information due to fundamental limitations. The development of automatic tools is ongoing. With the Santable tool, we realized a semi-automated striation counting tool, which delivers really highly reproducible, operator independent and cheap and fast results at the end. And yes, concerning the variable amplitude loading, we are really looking for fully automated systems to allow improved and simplified counting of fatigue striations. Yes, and again, the closed loop stress analysis material property is key for the quantitative fracture analysis, because it's not more possible really to do that alone and to give the results. Thank you.
Thank you.